Good afternoon, all of you. Welcome to the live session of Basic Linear Algebra week 4. Let's start with the summary of what have been discussed in the recorded session by the professor in week 4. Along with some true or false questions. So we saw that for n by n matrix A, it is invertible if and only if it is a full rank. That is rank of A is a size. Then what was discussed is if you have a vector u with components A and B, and if you have a vector v with components C and D, then determinant will actually give you the area of the parallelogram formed by these two vectors. So area will be AD minus BC, and a few properties were discussed on this area. So one property is area of parallelogram with u and v vectors. If it is 0, it means that u and v are coinciding. Another property is area of parallelogram with u and v vectors. If one of the vector is multiplied by a scalar, then you can bring that out. The scalar, you can bring it out. Similarly, even for the other case. And another property is if you have some two vectors, linear combination, some combination, linear combination, then you can write it as so this I discussed in the class. So based on this, tell me a true or false question. I am saying area lambda u lambda v. So this is true or false? So what do you think? This is true or false?
False.
Yeah, so what is the right statement?
Lambda square of the area.
Lambda square.
Yeah, so area, so these two are so anyways, these two are same, but here you have area will, the area will be, it will be like this, u and v. So this it has to be lambda square. Here it will be like lambda only, here also lambda, but here it will be lambda square. So that's not a true statement, it's a false statement. So similarly, as we discussed here, even here we have even here it is u1 plus u2 and we got a linear here, and even if it is u comma v1 plus v2, even then like it will be like area of p of u comma v1 plus area of parallelogram u v2. And some properties of determinant were discussed. So determinant of a matrix A will be equal to 0 if any row of A is equal to some other row of A, where A is not equal to J. So if there are two rows and we have same rows, then we'll have the determinant as 0. And if any row of A is a linear combination if we can write a row in a linear combination of some two different rows, then determinant of A will be equals to where dB is having okay, we'll discuss this in a detail a bit later. So what I mean to say is if you have a row in a matrix and you can express it as a one of a row, you can express it as a linear combination of two different rows, then you can express the determinant also as a linear combination where dB is determinant of the matrix. All the rows will be same, but here the row will be Ri dash and dB will be dC will be determinant of a matrix where all the rows will be same, but the is a linear combination. We'll see some questions on this. So someone is asking a question saying yeah, sessions are recorded and where can you watch it, means you are getting mails from NPTEL team, right? Where you are given the link also for these are uploaded in the YouTube, so you will get a link also from the NPTEL team itself. I hope you are getting that. So if you see those mails, you can find a link there, and that will be giving you the recorded version of this version of this live session, and also whatever this notes I am writing here, even the link for those also are shared to you by NPTEL team. I hope you are seeing that. So if you have any doubts, please stop me and ask. And determinant of identity matrix is 1. And what happens if you interchange or interchanging rows? The determinant will become negative of it. So if you interchange a row, so if you get a matrix B on interchanging any rows of A, then you'll be getting negative determinant. So answer a true or false question. If rows are linearly independent, if the rows in the matrix are linearly independent, then determinant is always 0. Is it true or false? If
False, ma'am.
then what is the true statement?
If rows are linearly dependent, then determinant.
Yeah, so if it is dependent, then determinant is always 0. Because the dependent rows you can write in terms of the other rows, and So if you have two same rows, as we said here, if you have two same rows, then you will get it as 0. And answer one more question. If B is obtained from A by replacing jth row of A by alpha into Ri A plus Rj A for some I which is not equal to j, and alpha is some real value, then so this is true or false statement. So this is true or false question. What do you say?
True, ma'am.
It's a true statement. So how can you find it is, for example, you have a matrix with Ri row and Rj row, and you're getting B matrix where replacing jth row with alpha Ria plus Rj. So what you can how can you write this? So as we saw here, when you are you can express it as a linear combination. So determinant of determinant can be expressed like Ra alpha Ra plus Ra Rj, and here they are linearly dependent, right? So determinant of this thing, so determinant here will be equal to 0, and Ri and Rj, and same as determinant A. So determinant B will be equal to determinant A. So this is a true statement. Apart from that, determinants of in the session in the recorded session we have seen determinant of elementary matrices. So we have three elementary operation matrices like interchanging rows and adding two rows, or multiplying a particular row with some scalar quantity. So what is the determinant of the elementary matrix which is for interchanging of rows, that will be equals to -1. So interchanging rows will be giving you determinant as -1, and so determinant of identity matrix is 0, we saw, right? Determinant of identity matrix is 0, and if you interchange any rows, then you'll be getting determinant as -1, because as we saw before, on interchanging rows we are getting -1 into the determinant, and if you add any two rows, then determinant will be 1 itself. This also we saw. And if you are multiplying with alpha, what will be the determinant here? So you'll be getting alpha here. So based on this answer true or false question, I'm saying determinant of alpha into elementary matrix is equal to determinant of so this is true or false statement question. What do you say? So this means multiplying a single row with single row of E with alpha, and this is multiplying E with alpha, elementary matrix with alpha, and I'm saying the determinant of both will be equals to alpha. So is it a true or a false statement?
False, ma'am.
Yeah, it is false. Then so determinant, so this is true till here, but determinant of alpha into A, so that won't be alpha. That will be based on alpha into the size. Whatever the size of the elementary matrix, it will be that power of n. Okay. Okay. Now let E be an elementary matrix. And A is a m by n matrix. N by n matrix. Then determinant of product of elementary matrix will be equals to, so as we saw here, the determinant of elementary matrix here, they come out to be a scalar quantity, right? So we have only three elementary matrices here, and so their determinants will be either one of these. So they are scalar values. So you can easily pull out the value here. So you can say determinant of this product elementary matrix into A will be equals to determinant of E into determinant of A. Do you have any doubt in this? So for example, if I am having a matrix A here, and suppose if I am interchanging the rows of it, then determinant of the interchanged rows matrix will be minus negative of determinant of A matrix. And suppose if I am multiplying a row of A, with alpha, so basically this operation will be there. So I'll be getting alpha into determinant of A. Similarly, if I'm adding some rows in that, so on adding rows, determinant won't change, right? So determinant will be 1 into determinant of A. So I hope you understood this point. So with this, if suppose A dash is is a reduced row echelon form, such that we are getting this by doing certain elementary operations on A, then determinant of A will be 0 if A is invertible. I mean A is non-invertible, and if A is invertible. So this was also discussed. So what does that actually mean? So here it is like we get, so I'm writing the same here. So determinant, so as I said, elementary operations, you can pull it out. Okay, and so reduced row echelon form determinant. So when you so as we saw in previous classes, reduced row echelon form will be having if it is a full rank matrix, you will be getting identity matrix. But if it is not a full rank matrix, then there might be some 0 rows in the bottom. for the row reduced echelon form. I hope you remember this. So if you are given a matrix A, you will try to reduce it into you will try to convert it into reduced row echelon form, where if it is a full rank, you will be getting the identity matrix, and if it is not a full rank, then you will be having some zero rows in the bottom. So it can have only two possible cases, either if it is full rank identity matrix, or some matrix with zero rows in the bottom. So if it is 0, then the determinant is anyways going to be 0, right? So here it will be 0, so that's why I'm writing it here as 0. Okay, 0 if it is non-invertible in the sense non-invertible in the sense the rank of the matrix is not full. So if the rank of the matrix is not full, it means that you have some zero rows in the bottom, so the determinant will be equals to 0. So when you get this so you can say this as determinant of A tilde by determinant of ek, determinant of ek minus 1, determinant of e1, like that. So if this will be either 0 or this will be either 1. So if it is 0, then if it is non-invertible, then it is 0, or else it will be in this form. So I hope this is clear for you. So if there is a matrix U and it is obtained by interchanging two rows r times, like for example okay, so number of for example number of row interchanges required for a matrix U to convert A matrix to row reduced echelon form, then true or false statement. So A matrix is to convert a matrix A, r number of row interchanges are done to convert the matrix A to reduced row echelon form. Then the relation between the determinant of A and determinant of U I am giving as this. So it's a true or false statement. Is this true or false? Is my question clear? So I am saying that you have a matrix A, and to convert it to a reduced row echelon form, which I am giving name as U, I am doing r number of row interchanges. So the relation for determinant of U and determinant of A, I am giving it as like this, as you see here. So this is true or false?
True, ma'am. True, ma'am.
Okay, so actually it's a false statement. So for example, determinant of for example, imagine that I have a matrix A, and I did one row interchange. Okay, one row interchange, then what will happen? 1 minus 1 will be there. Okay, suppose I am doing 2 row interchanges, then again one more minus. If I am doing 3 row interchanges, minus 1. So likewise I am doing r row interchanges. Okay, so it will be like this. So you can get this down here also. You understanding this? Does not change, right? Both are same, right? Even if you're getting this here, the minus, 1 into 1 2 times it is means it will be positive number. So only the even if you are getting it here doesn't actually mean that doesn't mean meaning is not changed. Is it clear? It's not r minus 1. I gave you r minus 1. It will be true if it is dA is minus 1 r times of du. So you know how many number of changes in row interchanges, how many number of times you are doing, that many times minus 1 will be multiplied. Okay. So E, so for E is so next question, for E is elementary matrix. Proof inverse of that. Yeah, try to prove this. Take a couple of minutes and try to prove this. So this is the identity matrix, A into A inverse, and if I am taking determinant on both sides, identity matrix, then it will be 1. And we saw that we can where is it? We can pull it out, right? When elementary matrix is multiplied, then you can it's just a scalar value, you can just pull it out. Is equal to 1, and determinant of, so that's why so thereby determinant of E inverse is 1. I mean this is 1 by determinant of E, right? Clear so far? Okay, so moving on. Okay, I'm giving two statements. Okay, so based on this, tell me one thing. Statement 1 is true. So you have three options. I mean, you have 4 options. One option is, I'll tell you the statements later, but option is statement 1 is true. Statement 1 and 2 is true. Statement 1 is true, but 2 is false. Statement 1 is false, but 2 is true. Statement 1 is true, and statement 2 also is true, because and the reason for why the statement 2 is true is because the statement 1 is also true. Okay. Okay, so the statement now is matrix multiplication of A is equal to matrix multiplication of AB is equal to BA. Okay. And statement 2 is determinant of AB is equal to determinant of BA is equal to determinant of A determinant of B. Yeah. So answer this question. So this what I exactly mean is this is like a reason and this is the effect like thing. Like statement 2 is true and the reason for that statement 1 and 2 both are true, and for 2 to be correct is because of the reason of 1. So that's what I mean. So try to analyze this and tell me the answer. Okay, is statement 1 is true?
No, ma'am.
Okay, okay, see, I made a change, small changes to option. Both are false. Okay. Statement 1 is not true, right? Addition is not commutative, okay? I mean, multiplication is not commutative. So we saw this last time also. What about the statement 2?
Determinant of AB is equal to the determinant of A into determinant of B because both becomes a scalar, but determinant of AB doesn't equal to determinant of BA, I think.
So okay, so I think so because you are sure the determinant of 1 is definitely false. So either option 3 or option 1, right? Dilemma in these two things. So we will see about determinant of AB, okay? So I am saying I have a 8 in the we saw that okay, so okay, so we saw that a matrix, suppose if I'm having a matrix A, then I can do some elementary operations like E1, E2, Ek, some elementary operations, and I can get it into the reduced row echelon form. Okay. So now I'm saying that even what you can do is start with reduced, assume that you already have this, and you are doing some elementary operations, some E dash, something elementary operations, all these things, and same elementary in reverse, actually same elementary operations in reverse you are doing, and you are getting it A. Okay, are you convinced with this? Like for example, if I'm having a matrix, and if I'm doing all the elementary operations to the matrix A, then to get the reduced row echelon form A theta, then I'm saying that you same operations you can. Okay, so let me clearly say this. So I'm getting this. So same thing in reverse, if I'm doing some elementary operations, same thing if I'm getting it here E inverse for example, then okay, so I can do some elementary operations to get actual matrix from the reduced row echelon form. Okay, so for time being I'm calling this as some fk minus 1 something. I'm calling all this matrix like this. Okay, so if I'm doing like this, I'm getting some A matrix. Okay, similarly if I am so I'm having this reduced row echelon form of B matrix, and if I'm doing some elementary operations. Okay, some elementary operations I'm going to get this. Okay, so now if I'm saying determinant, I'm saying determinant of for this I hope this is clear so far. So what I can say is these are all elementary operations, right? So I can pull it out. So here's one thing. Similarly, an AB matrix, for AB matrix, even for AB matrix, for example, there are some elementary operations. Okay, so what I can say about this is can I write like this? From this itself, AB I am multiplying, and I am getting like this. So what I can say here is, so I can pull them all out here also. From this we can easily say that determinant of AB is equal to determinant of and B. Okay. Now determinant of B and A. Wait, I think I lost it somewhere. 1 second. Okay, we'll get back to this in the last. So for now, you just remember. Okay, so for now, just remember that both these statements are true. But in a moment, in some time, we'll just get back to this. Okay. Let's not spend more time on that. Okay. So meanwhile, okay, we'll see some other things like what is inverse of A inverse of matrix. It was discussed that adjoint of A by determinant of A. Okay. And there were also something discussed like Cramer's rule. So which will help you to get the unique solutions of the system of solutions. You can use this method only if you know that there exist unique solutions. And one more thing is if you have a matrix A, a square matrix, and you want to find what is the rank of the matrix, then what you can do is first of all you try to find the rank of the whole matrix, and if it is full rank matrix, then the rank will be the size, and if it is not, then you will find a sub matrix. For example, if it is 3 by 3 matrix, then you will see all the 2 by 2 matrix combinations, and if any one of the 2 by 2 matrix, or that the rank for if it is a full rank, then I mean if it is determinant is not 0, then you will have rank as 2. Any one of the 2 by 2 matrix. If it is a full 2 by 2 rank matrix, then the rank of the whole A matrix will be equals to 2. Okay. So these are all the points that were discussed. So tell me one true or false statement. Determinant of A is equals to determinant of reduced to echelon form of A. It's a true or false question.
True, ma'am.
No, it's a false statement. See, determinant of
Ma'am,
yeah.
when I exchange the matrix A into the identity matrix, then say this matrix will be known as the row reduced echelon form.
Sorry. Please ask again.
When a matrix can be exchanged, argumented matrix A by I is equals to the matrix A will be exchanged to the I, then I can be converted into the A matrix, then the I will be known as this matrix will be known as the row echelon form A inverse.
So A augment I, you are saying this. I'm doing elementary row operations to convert this to I. Is that what you're saying?
Yes, ma'am. Yes,
And then
ma'am.
this will be. So what? I didn't understand. Okay, what is the question? I didn't get it clearly. I'm sorry for that, but could you please tell me one more time? Yeah, who was asking now?
Ma'am, in row reduced echelon form,
Okay, so if I have a matrix A, then row reduced echelon form, okay.
then determinant of A equals to row reduced माने determinant of A tilde ही होगा ना.
Can you talk in Hindi? मतलब नहीं होगा कि होगा मतलब false or true statement, whatever you are saying. Okay, fine. See, let me answer this question to you. So, see, A matrix is suppose you have some matrix here. Okay, you are doing all elementary row operations. Okay, something you are doing elementary row operations, and then you are getting this to A, and you are getting this A in the matrix. Okay, so I'm saying determinant of A. See, and then suppose it is identity matrix, for example. If you are getting this as identity matrix, then you will be having determinant as 1, right? But here you will be having some determinant, some value you will have, because you are not considering. I did not here I did not consider the determinant of elementary matrices in this statement. If you consider the elementary matrices also, then the statement might be true, but here I have not considered any elementary matrix. I am directly saying determinant of A is whatever reduced row echelon form I am getting. I am saying it's like that. So this can be 1 also. If it is 0, then that is different. If it is 0, then if it is a singular matrix, then determinant of A and both determinant of A tilde both will be 0, and then it will be for that this equation may work. That's a special case. But in a regular this case also is possible that determinant of A might be some number, and because this is a reduced row echelon form and it's a full identity matrix, then we will have only 1. So it's not true. It's a false statement. Okay, but if you consider the all elementary row operations, for example, if I'm saying all the elementary row operations are also coming, which is making that as this thing, reduced to echelon form, then this will be true. You understanding? Simply without this, it will not be true. Okay, solve determinants of a few questions. Okay, what is the determinant of this? what is the determinant here? First of all, what is the type of this matrix? Do you see any? Is this a special type of any matrix? Special matrix? Is this any special?
Lower triangular matrix.
It's a lower triangular matrix. So for a lower triangular matrix, what is the determinant?
Minus 60.
Yeah, it's minus 60. How did you do this?
I'm in first row, minus 3.
So minus 3 you are doing, and then 20 minus 20.
First row and first column will be.
Yeah. So so what I'm saying is when it triangular matrix, the determinant is just a product of diagonal elements. Okay, so diagonal elements, if you just product it, then you are getting the determinant. Okay, let's take one more question. Determinant of this. So what is the answer you got? So 1 into 12 minus 3 into 4 plus 4. So it's like 12 minus 24 is minus 12, right? Any doubts? See, I hope you calculated this determinant of this thing. Okay, so 1 into, so this I'm doing it by this row. So 1 into I'm finding the minor of this. So 6 into 2 minus 0 into 4. And then this for this thing minus 3, because the cofactor will be minus 1 here, so 3 into 2 into 2 minus of minus 1 into 4, and here anyways it is 0, so it is going to be 0, so 1 into 12 minus 3 into it will be 8, so it will be like 12 minus 24 is equal to minus 12. Okay, so I hope you understood this thing. Okay. Okay, let's get back to this question. Okay, so this was the question. So determinant of AB, okay, so we know that multiplication is not commutative, so AB will not be equal to BA. Now determinant of AB is equal to determinant of BA is equal to determinant of AB. Determinant of A into B. Okay, determinant of AB is equal to determinant of BA is equal to determinant of A into determinant of B. Okay, this is what I'm saying. So as I said, from A, if you are doing some elementary row operations, you can get 8 in the which is reduced row echelon form. Okay, and to the same reduced row echelon form, if you are doing some elementary row operations, again you can get back to A also. Okay, so I am saying that I am getting A by doing some elementary operations to 8 in the. Okay, and B also same way. Okay, now there are only two possibilities, right? So whether this is, if this is invertible, if A is invertible, then this can be either identity matrix, both A and both these two things, they either can be identity matrix or a matrix with some 0 rows. First let's consider this case. Okay, if it's identity matrix, okay, then I can say it like this also. It's as a matrix as a a product of some elementary operations. Similarly, like this. Okay, now I'm saying what is AB into can be a okay. So now determinant of A B will be equals to determinant of so which means I can write it as individual elements also. Okay, now what is determinant of BA? This is k minus 1. So this also I can write it as separately, right? I can pull it out. They are just scalar values. So ultimately you are multiplying the same elementary values. Okay, so that's why determinant of that's why I'm saying here determinant of AB is same as determinant of BA. And from here you can say that determinant of A will be equals to determinant of EK, determinant of okay, I'll write it in a separate. Determinant of A because I wrote here this thing. Okay, so determinant of A will be equals to determinant of all the elementary matrix multiplication. Similarly, determinant of B will be right. So ultimately this product these two are getting multiplied when determinant of A is multiplied by determinant of B. So ultimately you are getting the same product. So whether it is AB or BA or it's going to be same. Are you convinced with this? Till here, are you with me? Do you have any doubt? So I'll repeat this again, okay? So what I'm saying is that I'm getting the A matrix by some elementary row operations. Okay, so elementary row operations. For now, I'm saying that, for example, it's a full rank matrix, and I'm having this as identity matrix. So if I'm doing certain things to this elementary row operations, I can get A matrix. Similarly, the B matrix also. If B is identity matrix, and if I'm doing all these elementary operations, then I can reach to B. Okay, so I'm saying like this. Okay, so because this is identity matrix itself, I'm saying because the row reduced echelon form, it is a full rank, for example. Then I'm just like taking the case of the full rank for now. Then it's going to be like identity matrix. So I just remove this. Okay, so we'll get this as A as like this and B as like this. Okay, I hope you reached till here. Now if I'm multiplying AB, then I'll get this product of these two. BA first will be here and second will be here. Okay, now I'm trying to find the determinant of this thing, determinant of AB. So because all these are elementary row operations, and we saw a property saying that if it is multiplying by elementary operations, determinant of elementary row operations means they are going to give the scalar values only, so you can get it outside. So you can write it as a determinant of individual elementary row operations. So you will get the product of ek minus 1 e1 into the determinant of ek minus 1, determinant of e1 into determinant of fk minus 1, the whole thing into determinant of f1. So this product is not going to change on the right side if it is determinant of AB, determinant of BA, or determinant of A, determinant of B. So this will be true. Okay, so we saw the case when this is a full rank matrix, when this is identity row matrix. Okay, now this can have some zero rows. So for example, if I'm taking the case where one of the matrix, for example, among A and B, suppose if A is not a full rank matrix, for example, it's a singular matrix, then it will have a number of some zero rows in the bottom. Okay, so then what will happen now? Till here, is it okay? If you have any doubt, kindly ask me. So now if I'm saying, for example, A is singular here, okay, then so I'm saying I'm saying AB, okay, so for example EK I can write it in this way. Okay, which can be written as I got all the elementary operations outside. Okay, now for example, if this is singular, then it is going to have some zero rows. So the product also will have this thing also will have zero rows. So for example, if I'm having something like so this into this multiplied, So ultimately here also you will have a bottom row 0. Okay, product, suppose this is A tilde and suppose this is some V matrix. Ultimately the product also will have some 0 rows in the bottom. Okay, so determinant of this will be 0 of this thing. Okay, so here we derive that. So from here we derive the determinant of AB is 0. Okay, and anyways determinant of A into determinant of B, that also will be equal to 0, because determinant of A is 0 because you have this is not a full rank matrix, so it's a singular matrix. Okay, and then now let's see determinant of BA. How can you write BA? So I can write BA as FK minus 1, all those things, F1 B tilde into A. Okay, now determinant of BA will be equals to determinant of FK F1, all those things, the determinant of okay. So now again here the same thing. Okay, I'm having some okay, so okay, so again the same thing. Okay, so here you can write it as okay, so I told only A as I told only suppose only A is singular, I told, right? So this can be okay, so I told A is singular matrix, right? So here this is going to be anyways identity only. B tilde will be identity only. Okay, so okay, forget about this now. Determinant of FK minus 1, all those things, F1. Okay, so this is anyways identity matrix, so you can write B as FK minus 1 and F1. You know B tilde is anyways identity, so we can remove it, we can just leave it. And determinant of A matrix. Okay, and A is singular, I told, so its determinant will be anyways 0. So here determinant of BA is also equal to 0. Okay, so determinant of AV and determinant of BA and determinant of A, determinant of B will be equal to 0 if either of A or B is singular. So for any case this is going to be true. Do you want me to repeat this again? I mean, do you want me to repeat this? Okay, I'll just summarize it once. So I gave a question saying that statement 1, AB is AB matrix multiplication is same as BA, and determinant of AB is equal to determinant of BA and determinant of A and B. So we are seeing whether this is true or false. So this commutative law is not applicable for multiplication, so this is anyways false. And so 1 and 3 options, and now we'll see for this statement 2. So determinant of AB is BA is equal to determinant of A and B. So what I'm saying is some elementary row operations I'm doing to the so I'm taking one case, either I'm taking one case that both A and B are non-singular matrix. Then I can write A as the product of the elementary row operations. I can write a matrix as a product of elementary operations. Okay, any matrix. So A and B, I'm writing it like this, and I'm saying for now, for one case I'm taking now here is this this singular non-singular matrix. So the reduced row echelon form will be identity matrix. So now for A I am writing as product of the elementary operation matrix A and B like this here, and from here I am getting AB product as like this, product of these two, and BA as product of here first B and first elementary row operations corresponding to B and then A. So I'm getting it like this. So now determinant of AB is equal to determinant of the entire thing here, which we are getting here, entire thing. But these are all elementary row operations. Element matrix corresponding to the elementary row operations, so elementary matrices. So elementary matrices means the determinant will be scalars only. So you can just pull them out. So you can so you'll get ultimately this thing. And determinant of BA, even that you will be getting in this way. So this product will be same. And if you just multiply determinants of A and B, even then you are going to get the same thing. So determinant of AB, BA and determinant of A and determinant of B product all are going to be same. This case I explained for A and B is non-singular. And suppose if I am saying that one of these matrix is a singular matrix, then what I can say, AB is elementary row operations. I can get it some elementary row operations I'm getting to get this reduced row echelon form, and then into B, AB matrix, then determinant of AB. I can, these are the elementary row operations, so I'm pulling this out, and this is normal matrix, so I'm just keeping it like this, determinant of 8 into B. Then this I'm talking about this thing. So for example, if I'm saying A is singular, then I'll be having some number of rows 0 in the bottom. So the product also will have some 0 rows. So ultimately determinant will be equal to 0. So from here, if either of A and B, so if A is 0, A is a singular matrix, then determinant of AB will be equal to 0. And similarly for BA, so I can write fk minus 1 like this, and this is anyways identity matrix, because this is a non-singular matrix. So I can write B as product of elementary row operation matrix, and determinant of BA will be equals to determinant of fk minus 1 f1 determinant of A, and I pull this elementary row operations outside. So determinant of A will be equal to 0 here, because the last row is going to be 0. Okay, so last row is going to be 0 here. So ultimately determinant of BA also is going to be 0. So determinant of AB, BA and determinant of A into B is going to be 0. Okay, so we proved it for both the cases, if it is singular or if it is non-singular. For both cases this is going to be true. So the option here correct is 1 is false and 2 is true. Okay, so this is the right answer. Is it clear? Shall I proceed? Any doubts in this?
Ma'am, in AB equals to BA,
In AB is equal
then if first statement is true,
first statement is true.
then the determinant of AB is equals to determinant of A into determinant of B. Then determinant of a BA will also be known right as the determinant of AB, then determinant of A into determinant of B.
Okay, that's a good question. But what I can say here is, this is a matrix multiplication. I mean, this need not be true always. Okay, so
Ma'am,
so what I'm saying here is AB, if it is true, if for some matrix, for example, some special case is happening, and suppose you are getting AB is equal to BA, then determinant of AB is same as the determinant of BA, but this will be valid only for some cases, this is not true for all the cases. So for example,
for diagonal matrix it is true.
Yeah, so there might be some special cases for this, for which AB is same as BA, but it's not true for all the whatever matrices. For example, 3 by 3 matrices, you can take the example of some 3 by 3 or also maybe some 2 by 2 matrix, something like that. for example, if you are taking okay, let's do it separately somewhere last. So for example, if you're taking some 2 by 2 matrix like what will be determinant of the product of this? So this is A I'm taking, this is B I'm taking. This is the wrong example. Do you see this? The one who asked the question? I'm taking A matrix, I'm taking A as for example 1 0 1 1. This is what I took, A matrix, and this is what I am taking 1 2 3 4. Simple example I am taking, okay. So now I am doing AB. So AB when I am doing multiplying, so I am getting this matrix. And suppose I am doing BA, I am getting this matrix, and this both are not same. Okay, so AB is equal to BA is not true for all cases. So so for example, if you have a matrix of different size, like for example, if this is M by N matrix and this is N by P matrix, and then suppose A is M by N matrix and B is N by P matrix, and then the product you are going to get C as M by P matrix, okay. But if you are multiplying in reverse, so N into P and A is M into N, okay. So first of all, these two are not same. If suppose M is not same as P, then suppose for some matrices, if they are not square matrix, the rectangular matrix, then for them even the matrix multiplication itself won't be possible. So this as a whole, generic in general, if you are taking considering all rectangular, all those matrices, then this AB will not be equals to BA, so it's not commutative. But having said that, in case if there are some special case, some special matrix, for example, if A is some identity matrix, and then in that case you will get AB same as BA, then determinant of suppose if you are getting a matrix such that, suppose if this is true, then this will be true, okay. If this is true, then this will be true, but this is not true because this is true, reverse is not true. You understanding? If statement 1 is true for some reason, for some combination of AB, okay, and then the statement 2 will be true. But here it is like I said statement 2 is true because 1 is true, okay. So this will never be true because this is not true because this above statement is true. You understanding? The conclusion what I am trying to say is AB matrix is the matrix multiplication is not commutative. Certain times if you see in general all types of matrix, then sometimes AB and AB might be possible, but BA might not be possible at all for some rectangular matrices. So AB is not equals to BA in general, generic statement. It's not a property I'm saying. Commutation is not a property of matrix multiplication, okay. Property means it has to be true for everything, okay, everything. Then but there might be some special cases where AB is equal to BA, okay. In that case obviously this is going to be true, but though this is not true, this is going to happen. Am I clear?
Yes, ma'am.
So determinant of AB, I'm talking about square matrix here now. AB, determinant of AB is equal to determinant of BA is equal to determinant of A and B. This is true. But the reason is not this. This is not commutative, okay? So you have to be clear that you have to be clear in the matrix multiplication and determinant in the product of determinant of product of the matrices. I hope this clears some concept for you. So with that, tell me this is true or false. Determinant of alpha, C is okay, A is a matrix for example. True or false question.
Is it false?
Yeah, what is the truth statement? True statement.
Truth statement would be we must know the order of the matrix, and it would be if A is a matrix of order n, then it is alpha to the power n determinant of A.
Yeah, so this is true. This is true and this is false. Okay. Okay, find the determinant of so it's simple one, right? Cos of alpha, cos of beta minus sine of alpha, sine of beta. So you can say this as cos of alpha plus beta also. Okay. So it's a simple question also. So move on to the next question. So what's the determinant of this?
70.4 into 0.5 minus 1.9.
Sorry?
Multiplication of the diagonal element because it is an upper triangular matrix.
So did you get this? Okay, anyways, the logic is correct. Okay, so we'll move on. Okay, now this is okay, so this question you see. Determinant of this matrix. Can you just look at the matrix and directly say the
Antisymmetric matrix or skew symmetric matrix it is.
So that's the correct thing. Can you say directly the answer for this?
Zero.
So now I'm saying the statement. For skew symmetric matrix, determinant is 0. True or false?
Answer should be false.
Why? Here you're getting
Uh, There are two cases in this, no? If it is odd order, then it is 0. But if it is even order, then it can have any value as a determinant.
yeah. So determinant of skew symmetric matrix is 0 if the order is odd. But if order is it can be it's not 0 if order is even. So this is the skew symmetric matrix with third order. So we can directly say the determinant is 0. Okay, so why this happens? So skew symmetric matrix means determinant of A transpose is equals to minus of A. And A transpose is equals to determinant of minus A, and so minus 1 the order determinant of A. Okay, so you'll end up with determinant of A transpose.
We can replace determinant of A transpose by determinant of A.
Yeah, so if this is the odd order, for example, then if it is odd, n is odd, okay, then determinant of A transpose is equal to minus of determinant of A. So this will be true only if it is 0. You understanding? You know when you have a matrix A, okay. So basically the rule is when you have a matrix A and A transpose is just you're interchanging. You're just transposing the rows of you're making the rows into column into rows. So that won't change the determinant. Okay, so determinant of A is actually determinant of A transpose. But in this case you are getting as determinant of A transpose is minus determinant of A, and this is true only if determinant is 0. 0 is equal to minus 0 like that. Okay, and for example if order is, this is because order is odd I am saying, but if the order is even, then determinant of A will be equals determinant of, this is a positive term, determinant of A is determinant of A transpose. So A transpose, determinant of A, both are same, so that's a true statement, so it can be anything, any value. Okay, determinant of this matrix. I'm giving multiple examples so that you will get a hands-on experience, because when you solve, then only you will tend to notice the type of the matrix. Like for example, here it's a skew symmetric matrix, and here we had lower triangular matrix. So you will tend to notice. So simple example, but try to solve. That's simply like u into u square minus vw minus v into uv minus v square plus w into will give VQ minus VQ plus so I hope you can get this. So moving on to next question. What is the determinant of this?
It's determinant of 1, 2, 3, 4 and into determinant of 5, 6, 7, 8. Block matrix. Minus 4.
Minus 4. Now
Sorry, plus 4. Plus 4 it is.
So what do you see? Answer is 4. Even if you open, if you go by row wise, so you'll be getting answer 4. Okay, let's move on to the next question. So first, using Cramer's rule, find xy. So first of all, can you apply Cramer's rule for this?
Yes, ma'am.
How can you say that? How did you say that?
3 equations and 3 unknowns it is. No?
3? I didn't get you.
We can find out the values of x, y, z as x is equal to determinant of this matrix 0, 3, 4, 4, 3, 2. That would be in the division, and to find out the numerator, we have to replace the column of x by the right hand side
First of all, you have
elements.
to check whether you can apply Cramer's rule for this or not. So you have to find the first determinant of this matrix.
Determinant of coefficient matrix should be non-zero.
Yeah. So first of all, you have to check this. If it is 0, then again you cannot really find anything. Okay. And then you have to find the value for this, and then x1 you will get by determinant of replacing by determinant of a, and x2 you will be getting as you are just replacing you're just replacing this column by coefficient matrix. I mean this the augmented matrix. For example, if this is a B and this is A, so the corresponding column, so x2, this for x, for example, if it is A into x1, x2, x3 is equal to B matrix, Then if you want x2 second component, then you will replace the second column with the b vector b column, and then you'll get it. If you solve it, you will go. So I'm replacing second column, and then again determinant of a. So determinant of a is in denominator. It has to exist. It should not be 0.
Minus 87.
Yeah. So determinant of a is minus 87. So x1 so it is easy for you if you're doing hand calculations. It is easy for you if you open by this row, like 14.8 into 10 minus 1 plus 6.3 into, if you go with this first column, then it will be easy for you. And x1 is 104.4 by minus 87, that is going to be minus 1.2. And x2, determinant of 0, 4, 1, 14.8 minus 6.3, 13.5, 4, minus 1 by minus 87. So now I'm going with the second column. So first of all, cofactor you have to be careful about. Minus 14.8, 20 plus 1, and minus 6.3, cofactor is 1 for this, into minus 4, and minus 13.5, cofactor is minus 2, to minus 60. Ultimately, if you solve, you will be getting minus 69.6 something. Then minus 69.6 by 87 will be 0.8. So this is x2, and x3 if you solve, 0, 3, 14.8, so 2 minus 6.3, 1 minus 1, 13.5 by minus 87. I will give you 40. I'm going now by column 3, expanding determinant. So entire thing by minus 87, you will be getting 3.1. So x1 will be minus 1.2, x2 will be 0.8, x3 will be. So this is actually a lengthier version of finding the solution. And Cramer's rule you can only use if the determinant of coefficient matrix that is non-singular. If it is a unique solution, then only you can find it. You can apply Cramer's rule. Okay, moving on.
Ma'am,
Yeah.
with the help of Cramer's rule, we will be always getting unique solution.
No, yeah. With the see, you can apply Cramer's rule only if you know that you are going to get unique solution. So first of all,
Okay.
you have to you will get only unique solution. You understand? Because for example, if you have infinite solutions, it means that what did we discuss before? If there are if we have this two matrix, augmented matrix and the coefficient matrix, then if rank of A is equals to rank of A augment B, and it is equals to number of
Unknowns.
unknowns, then you will be having unique solution.
Unique solution.
And if both are same,
Less than n,
But,
infinitely many solutions.
yeah, but if it is less than n, then you'll be having n minus r arbitrary constants, and you will arbitrary variables, and you'll be having infinite solutions. And if these both are not equal, then no solution at all. Okay. No. I mean, if rank of A is less than rank of cannot be more, definitely either equal to or less than, then no solution at all. So what does this mean is not a full rank. So if it's not full rank, then you cannot find it. You will get determinant as 0, because if it is full rank, then you will be getting if you try to convert it into reduced row echelon form, you will be having identity matrix. You will be getting full. But if you are this is not full rank, then you'll be having some zeros when you do a reduced echelon form. Am I clear so far? Is it clear for you?
Yes, ma'am.
So so you cannot determinant is in denominator here, so you cannot it cannot be 0. If it is full rank, which means it is having unique solutions, then only you can go for this Cramer's rule. Moreover, this is
Okay,
linear
ma'am.
way of finding. Okay, so what is the rank of this matrix? Okay, so what? Okay, so it's a rectangular matrix. So maximum it can be 2 rank. But if you see here that if you see any submatrix of this thing, then for example, if you see this, if you're taking this thing, then this, if this into 4, the second row into -4 will give you the first row. And for example, if you take this 2, then even here also, if you multiply this by -3, then you can get the third row. Okay, so and for example, if you take this 2, even then these two are linear combinations, right? So you cannot get even 2 by 2 matrix. Even the 2 by 2 matrix, if you see all the cases of 2 by 2 matrix, for that also the rank is they're not full. Rank of submatrix is not full. Rank of submatrix of 2 by 2 size is not full, any of them. So rank will be 1. Okay, is it clear? You can do, of course, if you find the pivots, then only one pivot you will have in this, so rank will be 1. Even that way you will do. These are different ways of finding the same thing. Like rank you can find by converting into reduced row echelon form, or maybe you will see the submatrices, and then you can you will calculate with determinant, and for example, this is first of all, this is rectangular matrix. So for this you have to rank will be minimum of m and n. So you'll see all the 2 by 2 matrix, and if at least one is full rank matrix, full rank, then the rank will be of that order. Else it is lesser. You have to see the lesser submatrices of even lesser cells. So what is the rank of this matrix? For example, if you are saying this thing, then okay, so I'm getting some value here. So the rank will be 3. Okay, I am able to find one matrix which is one submatrix which is having full rank. So rank of this matrix is 3. Okay. Now prove this. So how can you prove this? So I'm taking inverse. I'll be getting identity matrix. And for now, for example, if I'm multiplying A inverse on this side, then A inverse here, and this is going to be identity matrix. So I'll be left with, now I'm multiplying C here on the left hand side. This also is identity matrix. Fine. So AC inverse will be C inverse, A inverse, likewise any number of matrix. A, B, C inverse will be C inverse, B inverse, A inverse, like that. Okay. So this is true or false question. Determinant of A inverse is equal to 1 by determinant of A. True or false?
True, ma'am.
Yeah. So here I can say is determinant of A inverse is same as determinant of A inverse, which is equals to identity matrix determinant, which is equals to 1. So determinant of A inverse will be equals to 1 by determinant of A. Okay, that's true. Okay, one more question. True or false?
It's true.
Yeah, so A square inverse, you can say it as A into A inverse, and which means A
Reverse law, A inverse, A inverse, A power
minus
minus.
A inverse whole square, right? or false? Inverse of transpose of A is not equal to transpose of inverse of A. So let's convert these words into so transpose inverse of transpose of A is not equal to transpose of inverse of A. Okay, so I am saying this true or false. So just take a moment. Okay, so A inverse is identity matrix. We know that. Now I'm taking transpose on both sides. I inverse transpose is again I only. Now AB transpose, this is a property that B transpose A transpose, right? So this I'm writing as A inverse transpose A transpose is equal to I.
It's true.
So this is true, you are saying. Inverse transpose, and I'm taking this. So I'm multiplying on this side by inverse. So A transpose inverse, and this will be identity matrix. So that will give me A inverse transpose is equal to A transpose inverse. Okay, so they are equal, so this is false. Okay, one more thing. True or false?
True.
Yeah, so that's again quite simple. A inverse is equal to I. Inverse on both sides, then again I will get I itself here. Then A inverse of inverse will be I. Which means A into A inverse. One second.
I can be written as A into A inverse.
Yeah. Sorry. Yeah. So let's take one last question and wind up. Simple matrix. Find inverse of this. Try to do with adjoint of A by determinant of A. So what is determinant? You can simply say
minus 2.0.
Yeah, so determinant is minus 2. So adjoint of A, for that what you will do, you will first find the minor, then cofactor matrix, then transpose of cofactor matrix will give you adjoint, right? So so here for first minor will be 4, and then the second minor will be 0 itself, third minor will be 0, and yeah, I think it's a quite simple thing. Take up another last question. Minus 1, 1, 2, 3, minus 1, 1, minus 1, 3, 4. What is the inverse? So first of all, what is determinant?
Twelve. Seven, minus 11, and 16. The second one should be minus 1, it would be. Correct. You are right.
So for 1, the minor matrix will be 7, right? Minus 7. Minus 7, and then for this 1 it is 12 minus 13, and then for this it will be like 8, and this is a minor matrix. So it will be like 4. So minus 2, and again minus 2, and then here 1 plus 2 will be 3, minus 1, minus 6 will be minus 7, and 3 will be minus 2. So this is the minor matrix. So cofactor matrix, that minus 1 into minus 1 into I plus j, if you multiply with minor matrix, you will get a cofactor matrix. So cofactor matrix will be minus 7, minus 13, 8, then 2, minus 2, 2, and then 3, 7 minus 2. This is cofactor matrix, and you have to transpose this. Minus 7 minus 30, 8, 2 minus 2 minus 2, 3, 7 minus 2, and this is a cofactor matrix, transpose, and determinant is 10. So minus 0 0.7, 0 0.2, 0 0.3, minus 1.3, minus 0 0.2, 0 0.7, 0 0.8, minus 0 0.2, minus 0 0.2. So this is inverse. So any doubts so far, or in the before classes?
Ma'am, I have a question.
Yeah.
Madam, there was a question in assignment number 3, and the results were declared,
Okay.
but I have posted a query on discussion forum regarding that question, but no one replied there.
Okay. So yeah,
So
you can ask.
that question is, if A is a real square matrix having full rank, then the row space and column space of matrix are equal. But that is not in general true. But
Okay.
whenever we have a
What is the
symmetric
question? I think,
matrix, then
did you
only
ask
it is
any
true.
question last time also? If every vector space has non-zero basis, something like that.
Yes, that is clear. That is clear.
That is
That
clear
is
for you,
for
right?
assignment 2.
Yeah, that
This is
question
regarding
is that.
assignment 3.
Okay, fine. That question is clear for you, no? You don't have any
Yes,
doubts.
yes, ma'am. Yes.
Okay. So what is the question now? I'll try to
If
answer.
A,
If at all I'm not able to answer, at least tell you the next class. Okay. So
okay,
if A is real square matrix.
square matrix having full rank,
Huh.
then the row space and column space of A,
Huh.
then the row space and column space of A are equal. Actually, you have taken this type of questions in the discussion also, and we have seen that in general it is not true. Row space is different and column space are different, even if we have the full rank. But if we have the symmetric matrix, na, then only it is true.
I think they mean by the rank of row space and column space. What is the
No,
answer?
no,
Because
they are
answer
not.
is
They are not just asking about the rank of row space and column space. They said the row space and the column space, which is not true. If you talk about the rank, then it is true, but it is they are not explicitly written there. The row space and column space. Rank nahi bola na.
So if
It
you are
is like
getting
row space and column space.
so if you are getting a square matrix and it is a full rank, so meaning you are getting a 3 pivots, then
So it is
meaning you are getting
the
3 pivots.
row reduced form of row, row reduced echelon form of a capital A is going to be identity matrix because it's a full rank.
I think this will be
So
true
if it
only if
is
it
a
is
ident-
symmetric, no?
having full rank mean RRDF has to be identity matrix.
Yeah,
So
that
if you have if it is a row reduced echelon form is identity matrix, so at least you can understand that if row reduced echelon form is same for a matrix. Okay, if it is identity matrix, then you can see now that row and column space and row space are equal.
So okay, so if a matrix is full rank, you know that it's a full rank. Then all the for example whatever rows, for example RJK, for example 3 rows I'm having, whatever, everything will be row space, and column, because you are going to have pivot in every column and in every row, because you don't have any zero rows here. So every row will be every row will make a row space, and every column will make a column space. and columns and rows need not be same, right? So I don't think this is true. I think this is false only.
No, because you are getting Rn in both the cases, n cross n matrix, right? So in both cases, row space is also generated by these n elements, and n such rows, and column are also generated by n such columns. So Rn it is going to row space is Rn, column space is also Rn.
No, column space, how can column space and
We are
row
saying
space
about
be same,
basis.
madam? Because
Basis
in
can
row
be
space,
different.
we see the pivots, and pivot element, with the help of that, we write down the column space. So in general, if the matrix is symmetric, then only it is possible. Otherwise, it is
No.
not
Here
possible.
rank is full, na. There is no zero row. So every column is a pivot column, and every row is like there is no zero row.
Okay, so
If
what
you
I
can
okay,
take a
so
problem, that would be okay.
yeah.
But I suppose that question, that statement is false.
Okay, so what I'm saying is okay, ABCD.
Mm.
Suppose you're saying something. Okay, you're getting like this. Okay. So what I actually
Yeah.
mean is, so for example, I am converting it into row reduced echelon form. Then ultimately, because it's a full rank matrix, so I'm going
We
to
are going
get
to get
this thing.
identity
Okay.
matrix.
Yeah. So I'm having pivot in first row, second row, and third row. So my A, B, C, my D, E, F,
All are the spanning.
and my H, I, J. These are my three basis for row space. And for my basis for my column space,
ADH,
will be
BEI, and
A,
CFG.
D, H, and because I have pivot here, so corresponding column here, so ADH, BEI, and CFJ, right? So these are not equal, no?
Yes, that is what I am saying, ma'am.
Basis vectors are different, but both space are three. It is.
Yeah, that's what. So I'm saying that's what is rank. We are not talking about rank, no?
No, but space is also same. R3 it is.
No, when
R3
we
in
talk
R3.
about space, that is okay. You the row space and column space must be in
Yeah, so
R3.
row
That is
space.
okay. But the elements
No,
are
they are
different. We
same.
cannot say.
Rows elements are will be different. No one saying that. As a vector space, they are same. Row space means vector space generated by rows. Okay, now you have what is so it is three rows are there. They are linearly independent. Okay, so they will span R3.
They
Correct or
won't
not?
span R3.
Yeah, they will
I
they
mean,
will
they are
generate the
in the they will be in R3, but they won't span everything in R3, right?
no, but A is a matrix from R3 to R3.
Yes, R3. So, but R3 doesn't just mean the vector space. You will get a vector space from the basis of row space, which will be in
Yeah, that
R3.
is what is row space is, no? Row space is generated by rows. And
Yeah.
column space,
So
we are only talking about this.
you have row space, you have
Yeah.
basis, you have vector. Okay,
Yeah.
you have vector space.
Yeah.
Okay, so what I'm saying is this is basis. Okay.
Yeah.
So with all the linear combinations, so alpha into with alpha into ABC, alpha into
You can
A,
see it is in R3, right? There are only yeah.
yeah, alpha into RBC, so all these things, whatever, these three things, gamma, whatever. So you'll get a vector space. Okay, you'll get a vector space,
Correct.
but R3 means
Hmm.
much more than that. No, in that
What is R3?
R3 means the vectors with three components. Anything, it can be anything. But here,
Yeah, so it is here it is anything. They are
no,
so
no.
you are getting three linearly
So
independent
one second.
vectors,
So it will
three
be
linearly independent vectors where each component there are three components, right? And you are getting three linearly independent
true.
vectors.
That is
In
true.
R3, what is
No, but
so
here,
it has to be
no,
R3.
no, no, no.
Yeah.
You will get here like A B C D E F H I J. Okay, so
No.
this
Vectors can be many. So they see basis vectors can be anything. There are a lot of basis vectors, infinitely many basis vectors possible. But what is a space? They have asked row space and column space. So row space is going to be R3 itself, because here it is 3 cross 3 matrix you have taken. No, it cannot go beyond that.
Okay, so what I am trying to say here is, okay, so what I'm trying to say here is, you will have, this combination. I'm not complete. I hope you will understand this.
Yeah.
I'm not completing it. Okay, I'll complete this better. Okay,
Yeah.
so the vector space, which is spanned by these vectors, will be in this form. Okay, but
Correct.
R3 can have a vector which is not in this form also. So it's a subset.
It has to be.
This is a vector space. It's a subset. R3 is a bigger one, and that in that vector space, there can be many vector spaces in this R3, not just this.
Acha, do you believe that if a matrix has RREF, like two matrices have the same row reduced echelon form, so then they generate the same vector space?
Sorry?
So see here RREF, if you the RREF a matrix, capital A is the matrix, and correspondingly it has the A tilde, which is RREF. Okay, so do they generate the same vector space, like same row space for A tilde and A? Do they do rows of A and rows of A tilde generate the same row space? It is going to be generating the same. If row echelon form is same, okay. Anyway, so fine. Might be like I could understand. Probably you have to think about this a little bit more. Maybe I'm not able to explain it because it is R. See, it is R3. You are not considering anything in R4 or R5. See, in R3,
what is R3?
if you R3 means
What
any
is,
linearly independent.
What is
See,
different
R3
in R3
means
in vector space?
R3 is a special kind of a vector space. That's a particular example.
No, that's what. Okay, so I can tell you some. Okay, so I'll open some book. Okay, so sorry, just give me a minute. I want to explain this to you.
No, you can maybe later on also because it's already 5 o'clock.
Yeah.
So maybe next class also you can.
Manideepa ma'am, actually you are mixing two different things: row space, column space.
Can you see here, for example, this question?
Spaces.
Okay,
These are
R3,
two different things.
all vectors in R3. Okay, so is the given set of vectors is a given set of vectors. I discussed this kind of questions before. Is a given set of vectors a vector space? All vectors in R3. Okay, with this condition. So R3 means R3 is R3 means all the vectors A, B with 3 components, everything.
Yeah, A, B, C.
Yeah.
Where A,
space,
B, and C belongs from R. Can be any real number.
But vector space.
Correct.
Vector space. It is formed from the basis of the vectors which is having any conditions like this. Okay. So condition is imposed.
Yeah, correct.
Yeah.
Linear combinations. Yeah.
Yeah. So what I'm trying to say here is this. There can be vectors which is beyond the linear combination also in R. You're understanding. R3 can be anything. Anything. I don't care. It can be anything. Okay, it can be
correct.
any number, one, whatever number. I'm not saying any number.
Any triplet.
Any number.
Triplet.
But that necessarily need not be in this form. Okay, so it necessarily not be in this.
I'm saying I'm concluding that it has to be. So the person who is asking that row space and column space are not equal, then if it is not equal, then he or she should be able to give me a matrix which is having full rank, but the row space and column space are not equal.
Madam has already given an example having a matrix A, B, C, D, E, F, G. Okay?
Yeah, that will not. You can continue. See, what I am saying about this here, row space, row vectors and column vectors, they will generate the same vector space.
Madam, actually
so that means
mixing two things: row space, column space, and vector space.
No, I'm not mixing.